Let me recall last time. Okay. There was this notion of definable set. So let me recall very quickly. This is L structure. And this is L formula with n free variables. Then it gives a definable subset of M of universe to Cartesian power n, given by those n tuples, such that if we plug the n tuple for these three variables, the formula holds, the sentence which was obtained like this, holds in this structure. So this is the set of n tuples such that in M phi of A is true. So this is called definable set. In the structure over some parameters maybe, and if phi has no quantifiers, then it is quantifier-free definable set. And actually we aim to describe quantifier elimination, so this distinction will be important, and also this is the way it should be thought of. So this is semantic way of thinking of quantifier elimination. So all definable sets should somehow become quantifier-free definable. Yes, that will be the meaning. Okay, I gave this example of definable sets in. Okay, I gave example of quantifier-free definable sets in fields. So if K is a field, then we have this in Kn, the Zariski closed sets. Yes, it meant given by solutions consisting of solutions of polynomial equations. So they are quantifier-free definable sets. They are quantifier-free definable, but not all of them. So then we had constructible sets. They were Boolean combinations of Zariski closed. I'm recalling now what was last time, so I'm a bit fast. And actually a constructible sets in this context are exactly quantifier-free definable sets. Okay, for any field. So they come from this, okay?
What is the Boolean combination?
Okay, Boolean combination. So you apply operations like, actually these two are enough, but let's say intersection, union, and complement, if I didn't make this mistake. So take the something minus this set and get them all. Okay. So looking at topology, you also got open ones, but not only. You may intersect closed and open, for example, and take union. Okay. So this was explaining what is Boolean combination. Okay. So next problem for last problem session. Okay, rather easy, but how do the constructible sets look in the line, just in K? So if X, okay, so this is new. I think I finished exactly here last time. For X in K, X is constructible or quantifier predefinable if you want. So they are simplest possible. Those who are always definable, it means that X is finite or X is cofinite. Yes, of course, cofinite means that K minus X is finite. Okay, so finite sets are always definable by formula X equals this or X equals this equals this. If you take complement, cofinite are always definable, and we see that in case there is nothing more which can be defined without quantifiers. Okay, that's a problem for you. And it is easy. If you, particularly you have to start from this Zariski clause, see what happens, and then with Boolean combinations.
Going time for finite points, we will find the polynomial, right?
That's, yeah, I was thinking about other direction. So not even polynomial. So in any structure, I was saying you can find polynomial, but you can also say if X is ABC, then you can say in any structure. So that doesn't have to do with polynomials, really. Okay. Yes, because I didn't recall, but we allow parameters. It's always we allow parameters from the universe. Without parameters, it would be worse. The description will be more complicated, but we allow parameters. Example. Sorry, these were examples here started. This was example 1 last time, now example 2. Rather obvious if we have LO, this is order, structure. Okay, the same X, say, with some order, and we have 2 points in X, then open or closed interval is definable. Okay, it doesn't have to look like an interval really, which means it's a set of all X such that this is true. Okay, now some more interesting things. One can see that actual real order, let me use this a bit over precise notation, order on reals is definable in pure field. So even, okay. Yes, because we can define it that X is smaller than Y if and only if there is Z such that Y minus X is Z times Z. Okay, strict order, so I have to add that and z is not 0. Yes, so order is defined. Huh?
You define an order, and in structure there is an order. What do you mean?
In this structure, there, Thank you, of course. It was a typo. Yes, yes. Yes. Thanks. So the point is that in pure field we can define order. And now the stories we discussed a bit at the end last time. So first another problem for you. Okay. So I warn you, you should know one theorem to show it, I think. That n natural numbers, the set of natural numbers, is definable in the ring Z. But it's also good to think about it. How can it be possible that something which most likely you will not be able to show, that Z is definable in Q. Okay, so this is, so such things actually you never know from the first sight. It may be something very easy, it may be very difficult, or it may be even we don't know. So this is difficult. This is difficult. So it was proved by a woman, Julia Robinson. Julia Robinson. This Knight stuck in my Julia Robinson. Okay, definitely I don't know her. So for funny, okay. And she, in her proof, I copied from Jochen Koningsman paper. It was defined by, so it should be defined by formula with one free variable, and formula had a form first two universal quantifiers, then 7 existential quantifiers, and then 6 universal quantifiers. And then some polynomial. Equals. So you see, I was discussing last time how definable sets are obtained. You start from quantifier free ones, which is like this one without any quantifiers. And then by quantifiers, you either project, and this corresponds to negation, to existence of negation, either project the negation, then you can do other things. So here there are basically these mixtures of projecting, negating, and that many times and that many coordinates. That somehow came in the proof. I didn't look at the paper.
What is the point?
It's a pretty big one. I don't know. You may look at the paper. It has 14 variables, so I don't think I'll be able to write it. I didn't even check if it's written explicitly. Maybe it is in the paper. But it was improved, but recently, after 60 years. So first Poonen in 2009 did similar thing, but like without this part. Yes, yes, number theorist. So, okay, so in fact it is kind of number or even geometric problem if you think of number theoretic. So, the shape of it.
How many? 7 variables.
But two changes of variables.
2 changes from universal to existential.
But then Königsmann, that was his paper in Annals.
He gave a talk in the International Congress of...
Yes, probably about that. So probably to read about it, it may be good to read, okay, well, maybe all of them, but I was looking a bit at this one, which is geometric, and here it's a universal. I'm not sure how many, but just a universal formula. So. Actually, the point was to find the existential formula, which will be related with next story. So it's still open whether there exists existential formula defining it, but he gives evidence that it shouldn't. If some number theoretic Bombieri conjecture is true, then it is not existentially definable. And he gives also one-line proof that any existential definition gives universal definition in this case by some one, not complicated formula. So it's really.
What do you mean by existential?
So you would start with exists. So really projection of something like Zariski closed, but in. And here it's projection of complement of Zariski closed. So different. So this is still open whether it's definable by existential, but probably not. Okay, so this is story about Z in Q. Okay, then some negative results, which we will be able to see even that such things are not definable in complex numbers, because basically only finite and cofinite are definable. And also not in reals.
You wrote the problem 16 for any.
Yeah, but constructible, yes. And here I'm talking definable any. So constructible is quantifier 3, which may be a bit hidden. Yeah. So this is. But the point will be that in complex numbers, it has quantifier elimination, so it's the same. But in other fields, not necessarily, like in reals. Yeah?
For 6 and 7, does anyone imply the other?
No, I don't see any. Two separate results that actually each of these theories has quantifier elimination, and none of them I don't see any connection. In the way of proving, maybe on some level, but no general, no. Am I telling the truth? Okay, C is definable in R. No, still I do. So what? You can interpret C in R. And would it give you anything?
You can see in R, of course, but
still.
R doesn't see because order is definable.
What?
Didn't we define the order of by
We did.
multiplication? If order cannot be definable in C?
No, R is not definable in C, but C is interpretable in R. Which maybe helps, but still I don't see how. So I don't think so. And now maybe most interesting, which also I know least, definable sets in natural numbers. So in n plus nth order. So here, okay, I'm pretty sure that order is not definable using plus n times. Actually, in Z it still is, but this, I created this problem, but not in natural numbers. So here, as before, quantifier free definable sets are defined by polynomial equalities and inequalities. I mean, using this or equality. But their projections, so already one step from quantifier 3. If we add existential quantifier, we get something extremely complicated. So, but let me write this whole sentence. Their projections are already very complicated. So this will also show that whenever n is definable, then the structure has very complicated definable sets. So this theorem usually is given to Matiasevich. Okay, but he built on the work of the same Julia Robinson. I think there are many Robinsons, but I think the same Julia Robinson, Davis and Putnam. So these examples I will not be proving, and it will not be possible to do it quickly. Robinson. This kind of recursive description of the set, so every, which I will kind of define, recursively enumerable set is a projection of quantifier free definable set. And this recursively enumerable, I can tell you more or less what it means. Definable set in here, of course. Yes, and this X is recursively. So it's funny, if there is an algorithm which takes as inputs natural numbers, and it stops only at elements of X. So it kind of describes it, but you cannot really know it, because if it takes an element which is not in X, then it runs forever.
Yes.
So you can wait, but you will not know. Okay, so kind of absolutely it describes it, but in real life it's hard to do it. Okay, so if you're variable, if there is an algorithm, so I'm not saying what is an algorithm, and actually I always get troubles to understand it totally formally. If there is an algorithm, that will stop if it gets input X in X, but it will run forever if input so actually this is, I guess, pretty large class if you can somehow recursively describe some sets of natural numbers. They fit, I guess, into this. So it should be understood as a very, very large class of subsets of natural numbers. Huh?
This is Hilbert-Tan problem, right?
I will come to this. Not yet, but soon. Yes. So actually relations with Hilbert-Tan, exactly. So this theorem provided a negative answer to Hilbert-Tan, which I will state. The problem was natural. Find an algorithm which will determine if a given defined equation has solution or not. So one algorithm determining. Yeah, has a solution, so it asks whether there exists some numbers satisfying a polynomial, okay, usually over Z, but it doesn't matter much, and solutions in Z. And yes, like Fermat's last theorem. And okay, maybe without going to details, why does it give negative answer? Because this algorithm, not the kind which will run forever, it would have to really determine whether there is a solution or not, but there are recursively enumerable sets which are not computable. So maybe I just say what computable means. So computable is something better than recursively enumerable. There should be algorithm which really tells you in finite steps this element is in X or not. Okay, so I think, yeah, set is computable if and only if X and complement of X are recursively enumerable. Okay, and all of this together gives somehow the negative answer. Yes, because kind of you can find, okay, now maybe I'm not, but so these projections of quantifier redefinable sets, they correspond to this defined equations, and you're looking for their solutions, and there are some here which are not computable, so I guess this somehow gives the answer to this problem, but I didn't check details. But somehow my point is that, again, describing definable sets here, this was, I think, most complicated and already solving open problems from 100-something years ago. So it may be very, very complicated problem to find such. And actually the motivation here to look for, if we could find existential formula defining n in Q, then we would show negative answer to Hilbert-Tan's problem over Q, because the defined n is over Z. over Q, it's still open.
I couldn't understand.
So you could, okay, so I didn't say what is the Diophantine equation. Yeah, but it's a polynomial equation over Z, and you look for solutions in Z. You can change from Z to Q and ask the same question. And then it is open, we don't know.
Yes.
But if we found here existential definition of Z, that would be the proof that there is a negative answer here. Somehow by similar methods.
Oh, okay.
Okay. But actually the paper of Koenigsmann suggests that actually this is not true, which still doesn't show the opposite, so I guess here it's quite open.
There is no existential formula, it says.
Yes, if a Bombieri conjecture is true. Okay, so that's such kind of connections.
Existential formula, why it is say?
Huh?
Then I didn't understand the last part of your argument.
So the last was that if you formulate this over Q,
Okay.
and you are trying to show the negative answer, then apparently it's easy. It's enough to show that Z is definable by existential formula in Q for the negative answer of the rational version of Hilbert 10.
It's enough that this, but he wants the proof of it also.
Of which? Do you? No.
Onuncu problemi Q'da çıkıyor. Şimdi eğer Q'nun içinde Z'yi tanımlayabilirsen, sen Z'de olmadığını bildiğinden dolayı eğer Q için varsa Z için de oluyor, çelişki oluyor.
Yeah, so this kind of circle of problems here, but all related with definability. Yeah, actually, it's a nice mixture. One could learn about it more. Logic, number theory, geometry, and this computability all together. Okay, it's kind of... and all related to definable sets and determining them. Okay, so our aim now, last thing in this lecture, will be showing Chevalley Constructability Theorem. So, which says that if K is algebraically closed, then projections of constructible sets in some Kn are again constructible. Yes, so this way of constructing definable sets already terminates on the first level. Yes, so this is how geometers formulate it, and okay, they have more general statements about varieties or schemes and morphisms between them with the same conclusion, but let us look like this. So now the model theoretic part, so general definition, which is now syntactic, so we say that theory has quantifier elimination. If for any formula Vx with these three variables, there is quantifier free formula such that they are equivalent modulo this theory. So it's a logical consequence of this theory that for all x, by this bar I mean there are several of them, it's a tuple. For all x, phi of x if and only if alpha of x. Okay, so if you translate to definable sets, it means exactly that all definable sets in all models of T are actually quantifier-free definable. This is the same thing. So at the level of definable sets, this property means that for all models of T, all definable sets in powers of these models are quantifier-free definable.
Why?
Because each definable set is given by such a phi,
Yes.
and then you find this quantifier phi alpha, and it gives the same set.
How you can find?
If theory has quantifier elimination by definition.
Okay.
And also the other way. Yeah, the other way. Okay. So actually our aim now can be formulated QE, which stands for quantifier elimination for the theory of algebraically closed fields. Okay, so we really want to show it modulo some things. So I want to show you one general criterion for showing quantifier elimination, and we will apply it to ACF. Okay. So I need some facts. So first, fact 1. Okay. M is some structure, and okay. N and M is an L substructure, and we have a 4 and phi is a quantifier-free sentence with parameters from the smaller one then it holds upstairs if and only if it holds downstairs. Okay, so it's like saying that with respect to quantifier-free sentences, all extensions are elementary.
What is ACF?
The theory of algebraically closed fields. So you can say in the language of rings. So okay, so this is again things we skip. Induction on complexity of, proof, which we skip. Induction of complexity of formulas. Okay, but the idea is that if you have some equality, quantifier-free sentence is just like some equalities. So upstairs and downstairs, it holds the same. So, like C1n equals C2m, if and only if maybe a bit simplified idea, C1n, because it's a substructure. That was example of very easy sentence that two constants are equal, and that is the same in M in N. It's a part of definition of being substructure, but will be the same with all the relations and functions. It's checking upstairs, checking downstairs will not make any difference by the definition of substructure. And then you can make them more complicated. So this is this induction on complexity. But it really doesn't matter. Okay. So this is this fact which I wanted. So corollary. If T has quantifier elimination, then T is model complete. This means that, as I was saying, any substructure is elementary. Yes. Model complete means that any substructure is elementary, so it means this is true, but for all sentences. But if it has quantifier elimination, quantifier-free sentence is the same as normal sentence. They are always equivalent, so it automatically implies being model complete. Okay, and we already know that ACF is model complete. So as I said before, this aim is something stronger. We want to show something more. And for that, okay, I need a notion of type. So I may define it before the break. Okay, so this, in this moment it will get a bit technical. For structure and some n-tuple. So I want to define types in simplest possible way. So I will write where the types are computed. Type of this tuple in the structure M is just the set of all formulas which are true on this tuple M in the structure M. So such that M. So if you want to think in terms of definable sets, these are all definable sets, but now without any parameters, whose solutions, which contain this M. Okay. So actually it's an ultra filter in the Boolean algebra of definable sets, which we will not use. And then, so it's called type or complete type. And actually in model theory, it's the main. We use types a lot, and somehow the way the types behaves determines property of theory. And there are lots of, Number of types, yes. The way they interact with each other. So this type is like the idea of this element. everything this element satisfies, kind of. It's type, yeah? How? What type? This tuple.
Define an ideal element which doesn't exist by type.
Yes, so if you just think about ultrafilters, it will be like types of elements which may not exist in your model, but somewhere else. Like you can think about type of infinitesimal real numbers given by all definable sets, like intervals getting smaller and smaller with and without zero. This is also, but with other definition a bit. So a type, and you can find elementary extension of R where such elements exist, and this is basically what non-standard analysis do.
What does it mean? I mean, number of types?
What was them? Okay, that you could. So now you have this Boolean algebra of definable sets or formulas, and then you can count how many ultrafilters out there. And actually it's important how many over, then you change number of parameters and count these types. And is the maximal number will be, I guess, 2 to the, there is some maximal obvious number. If it's reached, it means theory is very complicated. If not, there are the stability levels and this relativization. Yeah, actually he did something amazing. He managed to, in some sense, classify all possible theories. Okay, I think one of the points was to find, so if you have a theory, you can look how many models up to isomorphism it has in a given cardinality. So you have kind of function from kappa to this number of models. And he almost, I think, found all possible functions, which took him like 100,000 pages book, and he developed lots of notions. And I think it's many around types, somehow type was the main, one of the main techniques there.
But there's a lot of combinatorics
yes.
around the type.
But we are not going there, but yes, this notion of type is pretty crucial. So let me just say before break, quantifier free type. It will be all the same, but just given by quantifier free. So this is quantifier free type. Which, okay, sometimes are also used. So actually, the criterion will be comparing these two types. Somehow quantifier elimination will be coded into comparison between these two things. So I guess it's time. Yes, let's have a break.